Today we're going to be talking about managing 3D coordinate systems with GeoCalc mode in Global Mapper and coordinating that against Geographic Calculator. My name is Sam Knight. I'm the Director of Product Management here at Blue Marble Geographics. With me today, helping out with questions, is going to be Billy Noble, who's an application specialist. Say hello, Billy.
Hello, everyone.
All right, and so today the topic is working with three-dimensional coordinate systems. So we're going to be focusing on primarily vertical coordinate systems. This is a very complex topic. There's interaction here between two different softwares. There are differences in how they appear. There's differences in how they behave from the stock global mapper behavior, what some folks are used to. Before they get into the more technically complex vertical coordinate systems. So there's a lot of interplay here that we're going to look at between some geodetics, between the application interface. We have plenty of time today for questions as well. The format today is you are in listen-only mode. If you have any questions, please do feel free to use the questions panel. It's part of the GoToWebinar interface here. Typically, you'll find that on the right-hand side of your screen. And today's session is being recorded. So if you have, you want to refer back to anything that we talk about later, typically just takes us a day or two, and we'll have this posted up on our YouTube channel as well. We have a few upcoming training opportunities if folks would like to go deeper with some of the topics we're going to talk about today. We have a global mapper and lidar module trainings both coming up on a couple of weeks in April. First, there is a global mapper. This is a global mapper focusing on the main parts of the application, your 2D cartography kind of stuff. From the 19th to the 23rd of April, and then a deep dive on the lidar module. So getting very heavy into the 3D portions of the app that we're just going to start to touch on a little bit here today, later in the month on the 27th to the 29th. Then beyond that in May, we're going to be having another applied geodesy and geographic calculator class. That's for those of you that want to dive really deep into the nuts and bolts of geodetics. How geodetics applies within anything we're doing, whether it's in the geographic calculator or in global mapper, or as we're going to see today, where we get into crossover between those two applications as well. If you have any interest in that, you'll see the URL at the bottom of the screen there. It's just simply bluemarblegeo.com/training. So today we're going to be starting off by taking a look at the Geographic Calculator. We're going to climb into its database, and we're going to be taking a look at how we talk about things like vertical datums, coordinate reference systems, and geoids, what each of those things actually are, how they relate to moving the ups and the downs that we want to get into here today. So we're going to get into the technical portions of that. We're going to take a look at interacting with those definitions, how we do that in Geographic Calculator, how we do that in Global Mapper, and then we're going to take a look at some actual examples, some workflow. What we're going to use today is a piece of lidar data. We'll take a look at performing a vertical datum transformation on a piece of lidar data inside Global Mapper using the vertical definitions that we're going to be getting out of the calculator. So before we jump into that, I borrowed a couple of slides from our geodetics training course because there are a lot of folks that know they need to get into these topics, but don't have some of the basic understanding of what exactly is going on here with a vertical coordinate system. So the geoid model is what we're going to be heavily interacting with here. A geoid model is essentially the practical application of a vertical datum. Really what a geoid model is it gives us a zero surface where we're going to measure our elevations from. Very commonly people throw around the term mean sea level or just simply sea level. A geoid model is essentially how we get there, how we get to that idealized surface. They are irregular, and this is one of the tricky pieces. We have a lot of myths that we sort of imagine over time in our minds about vertical systems, where we say, okay, sea level. When you describe sea level to a child, we say if we were to fill in all the oceans and bulldoze all the mountains, the nice smooth ball that we would have. But really, that idea of a completely smooth ball is the idea of the ellipsoid that we have here. And on our line here, you'll see the ellipsoid is our blue line. So a completely flattened surface, no lumps and bumps around there. Where we live is the terrain, the extremely irregular surface with the dirt and rocks and oceans and bathymetry and things like that. But that's not our reference. Our reference is not ground unless we're doing certain applications around flying, things like that. There are references that we refer to as above ground level, and that would be our terrain surface there. Where we focus with sea level and these geoids that we're going to be talking about is somewhere in between that. So the geoid is a irregular surface. It is very smooth still. It's not quite as severe as the terrain. It's more lumpy and bumpy than our ellipsoid, but it's less lumpy and bumpy than the terrain. Very commonly, you'll find the geoids somewhere in between the terrain and the ellipsoid, but that is not a rule. That is just a sort of a commonality you'll find in a lot of places where we have land. Sea level is much more complicated an idea than just simply in between those two smooth and rough surfaces. So sea level is really, it's just an approximation. So we're talking about if we were to stand at the ocean and measure the midpoint as the tides go up and down, the mean of that, of the heights of where all of the seas go as they rise and fall throughout the days on their tidal cycles. Mean is simply the middle of all of that over a long period of time. They wiggle around. Sometimes one tide is higher than another. Over time, they go up and they go down. We know sea level is measurably rising, so our datums are going to be changing and increasing over time. But there are also local events, localized time events, that is. Things such as the moon cycle can affect that. Storm surge can affect that. So what we talk about with a geoid is an idealized version of this concept of mean sea level that we have, this very smooth shape. Even within that, none of the models that we use when we talk about sea level are actually a perfect model. They're all just, averages and models over time. So what we have on the graphic here on the right is a representation of our NAVD88. That's the North American Vertical Datum of 1988, two measured mean sea level offsets around the southeast coast of the United States here. So all of these values that you see on this graphic are in meters. So here we have one that is very close at this particular tide gauge. It's only 1 centimeter off. If we go a little bit down the coast there, suddenly this one is 13 centimeters off in the other direction. We get down towards the Florida Keys and you see these are off by about 1/4 of a meter. So these are approximations of sea levels over many thousands of miles. These wrap around coasts of whole countries and things like that. They are all they're moving around throughout time. There are time averages. Local deflections are very important when we start talking about moving between models and actually applying these into the field. Much in the same way that folks that are new to mapping very often get confused about latitude longitude, thinking that latitude longitude is a single exclusive system and there's only one model. Vertical models have the same confusion. A lot of folks are under the impression that if they say, I'm on sea level, that means just one thing. When in fact, there are actually hundreds of different versions of sea level for different regions around the world. And that's what we're going to get into a little bit here as we start talking about the definitions in Geographic Calculator's database that we're going to be applying in Global Mapper. So to hop over here, we have our two applications that we're going to be dealing with. We have Global Mapper and we have Geographic Calculator. Now, Global Mapper has this little toolbar up here, and on my screen right here, it's on the second row. On your local installation, it may be in another place. Sometimes you'll find it a little farther over on that second row. But it's made up of these three buttons right here. The first one looks like a little graticule on a globe. Second is a little gear icon, and then the Geographic Calculator logo. If you don't have that, you can find that under the toolbars menu, and you'll see there is a GeoCalc option for the GeoCalc toolbar. Some folks turn that off before they get into using the calculator, and then you got to go back and remember that it's there to bring it back on if you become a calculator user at a later point. If you have a Geographic Calculator and you have a Global Mapper installed on the same machine, and the versions are synced up, then you can simply toggle this button right here, the Enable GeoCalc Projection Mode button, and that basically switches over to connecting into the calculator's database of coordinate systems. I'm going to toggle that off real quick. We're going to take a look under our configuration menu. You'll notice under the projection tools, this is our familiar Global Mapper projection list. With GeoCalc mode enabled, I'm just going to go ahead and click that back on. If you have data loaded in when you turn that on, it's going to prompt you that you need to restart Global Mapper to initialize that new library. If you have nothing, you'll see it just turns on right instantly. If we take a look back under the projection menus, you'll see that changes, and these all swap over to use the GeoCalc based dialogue. So the way of defining coordinate systems is a little bit different in there. We have some different terminology that gets a little bit more into the geodetics world as we bring in things like vertical coordinate systems and get into different types of transformations and things like that. Let's see here. So let's hop over and we'll take a look in Geographic Calculator. This is going to be where we start out. Let's see here. Billy, I think I see a question coming in
Yep.
about the versions. Yeah, it is. Oh, I see a couple of questions. Is GeoCalculator?
Yeah, it'll require a separate license from Global Mapper.
Yep, so the answer is this does require two licenses. So Global Mapper functions completely by itself with its own license, and Calculator is its own license. So they're two standalone applications. You don't need Calculator to run Global Mapper, but as soon as you move into the realm of performing vertical coordinate transformations, Calculator is indispensable. That's what enables three-dimensional coordinate system handling in Global Mapper. So it's what's going to unlock all of the geoids and things like that. Another question I'm noticing there off the side is, does it require any special versions? And these, because they are standalone applications, you do need to have compatible versions with each other. The Geographic Calculator database evolves over time. We base many of our geodetics on what's known as the EPSG database, and that is an evolving database of coordinate systems. It's effectively the de facto world standard for coordinate system publication. So as it changes and takes in new things and evolves over time, our software evolves to match it. And then Global Mapper and Calculator need to be synced up with each other. So there are every time we roll out a Geographic Calculator and a Global Mapper, there are synced versions that go together. The easiest way to stay on top of that is if you're on the latest version of both of them, they are compatible. So at the present time, the release version of Global Mapper 22.1 is compatible with Geographic Calculator 2020 Service Pack 1. And with each subsequent release, then they are resynced with each other as the definitions change. So in the Geographic Calculator, this is where we're going to be actually managing the coordinate systems themselves. So the geodetics database that is the core of the Geographic Calculator is going to be connected to by Global Mapper to get those definitions. So we're going to do the definition over in Calculator, and then we're going to use it over in Global Mapper. Under the data source menu, this is where we're going to get into the nuts and bolts of what actually makes a vertical coordinate system. So there's three main types of geodetic definition that we're going to be talking about here. The most basic of the vertical components is a vertical datum. This is where it all starts. So in the calculator, we're going to find that under the data source menu under Datum Definitions. And bring that in from off screen. I'm working on a second monitor here, so you may see me occasionally pulling something in from off screen. Within the datums menu, you'll see there's two distinct types. There are horizontal datums and there are vertical datums. The horizontal datum is the component that works with the projection or latitude-longitude system. A horizontal datum can also be used as a vertical datum in the context of what we call ellipsoid height. So if you deal with coordinate system data and somebody says, I've got WGS84 heights, they typically mean a WGS84 ellipsoid based height. So not actually a real vertical coordinate system, but it is a vertical system that is used. So if there's a lat and a long and a height that goes with that, and the definition simply says WGS84, that typically means an ellipsoid height. Under vertical datums is where we have things that are actually regional geoid models, and they're typically sea level based. So under the vertical datums category here, you'll see a long list of these used for all different regions around the world. So I'm going to scroll down here to one we're going to be talking a bit about today. For the example I'm going to use is the North American vertical datum of 1988. This just happens to be our regional national datum that we use here in the States. If you're from another country, then you're going to be using probably typically whatever your national standard is. And in some parts of the world, if you're working offshore, you might actually be working in a common world model, such as, let's get up here to the E section. You might be looking at something like EGM 2008, 96, so on. You'll see there's ellipsoid height in there as a container, some of the various European vertical reference systems and things like that. This is the most basic piece of the coordinate system. And the kind of goofy thing about a vertical datum is if we look at the definition, there's nothing there. This is one of the trickiest concepts to wrap your mind around if you're new to vertical coordinate systems. A vertical datum itself is just simply a starting point that has a name. It is basically a container that we agree on that is the name of our starting point. It's the basis of our system, but there aren't actually any parameters to describe it. The datum in a vertical coordinate system is important because we all agree it is. It's a little bit like cash that way. Where the vertical datum gets a little bit more teeth is when we turn it into a coordinate system. So back in the data source menu there, I'm going to go into coordinate system definitions, and you'll see a number of different types of coordinate systems. So geocentric, geodetic, projected, string, those are all our common horizontal type of coordinate system. That's where our lat longs, that's where all our projections live. And then we have a vertical group of coordinate systems. You'll see I have some new stuff at the very top level of my list. This is usually categorized. In my installation, I have some that have been added in that haven't been added to a folder yet. Beneath that, we have geopolitical organization, usually geographic first and then political boundaries beneath that. So continent level and then country level below that. We'll see the similar NAVD88 system that I pointed out before. You'll see that down under the United States. In this case, I've got NAVD88 height. You'll see I've got some NAVD88 depths. I've got some different units going on in there. And there's a little bit of variation in here, but they're all based upon the same base datum, the same starting point that we have all just agreed on as our starting point. So if I open one of those up, you'll see we actually have a few parameters in here to describe these. The main thing is the datum. So we're saying, yes, this is based on this particular regional datum. And then it also has a point style. And the point style is important as we start talking about different types of units. The point style contains the units, but it also contains the direction that we're going to be measuring. Vertical coordinate systems can be measured up or down. So we talk about elevation, or we talk about depth. So you'll notice the orientation is listed in there, up, and the unit of measure in this case is meters. Many of those variations you'll see, some might say orientation down and unit of measure, some type of feet. Those are all the variations that really separate out the individual coordinate systems. So there are many different variations of those systems, just like we have in horizontal coordinate systems. If you think about using something like a UTM zone, and some folks use one horizontal datum in that UTM zone. Some folks work in feet, some folks work in meters or other survey units. The same is true of the vertical coordinate systems. As well, each of these has a usage, and the usage is defined by basically a scope, like what is the purpose of that coordinate system, whether it's for geodetics or surveying and so on. But the really useful piece of that is an area of use. These tell us exactly where the bounds of a coordinate system are. And so you'll see this is a North American system that is defined for use throughout the United States. The blue polygons on there are representing where exactly those are applicable. Okay, so that is the sort of the start of our coordinate system, but this still doesn't actually have the geoid in it yet. And the geoid is the practical application of how we get in between those surfaces that don't actually have any parameters themselves. So in geodetics language, the geoid is really a transformation. It's how you get from one surface to another surface, because the surfaces we're talking about are really just ideas. So under the data source menu here in Calculator, you'll see coordinate transformation definitions. And as we did before, you'll see we have your base datum transformations, our horizontals for datums and parametric datums, and then we have some vertical transformations. The organization in here mimics the organization we have for the systems themselves, but you'll see some different object names in here. There are some transformations that do things like get us between the height and depths. And those are basically just a multiplier. If we're going from height to depth, it's just going to say multiply everything by -1 to flip it upside down. But then we have some actual geoids. So in the case of our NAVD88 system, we have all of these US geoid models of 96, 99, 03, and so on. These are all different versions of the same surface, the North American vertical datum surface. These are different iterations of how to get there from the ellipsoid height that everything is based on at its core. So if we grab onto, let's see, one of the most common ones that folks are used to working with in this country at this point is the US Geoid Model of 2012B. That was a transformation for quite a while from NAD83 to this NAVD88 surface based on data from the 2012B, was the second revision of it, transformation. So here's where we get something that actually has some grids in it. This is a transformation, in this case from WGS84 ellipsoid surface to NavD88 height. It's based on a series of grids, and the grids are a necessary piece in order to be able to use that transformation. These are pieces you're commonly going to have to download if you're planning on working with any of these particular transformations. As with any grid, there's an interpolation type. These are typically predefined by whatever the defining authority is, and that's usually going to be a national survey authority. And the path is simply the subfolder within the data source, the database of all of these grids on your local machine. So this is how Geographic Calculator is going to find these files. In this case, these ones all have a 12B extension on them in the vertical subfolder of your database. It's a transformation going between ellipsoid height on WGS84 and NavD88 surface. Now, if we see all of these other datums here, you'll see there are a number of different iterations of how to exactly do that. So we had some that were derived back in 1996, and then periodically up through the years, coming all the way up to our latest, which is 2018. Most of these are sea level based, and you'll see some that is a slightly different category here. You'll see these ones marked tidal. These are alternate sea level references. They are tide-based offsets. So they're not actually mean sea level. Some of these are, let's see here, say MHHW, that is mean higher high water, mean high water, mean lower low water, all of the various tide stages that are used in navigation and things like shipping channels and such. So the vast majority of these are mean sea level based. The ones that are tidal are marked as such. And in our database, most of those are going to be found around the US coast. There aren't too many publicly available tide-based systems for other parts of the world yet. Let's see. Billy, do we have any questions coming in at this point?
Yeah, we have a couple of good ones here. Someone's asking, maybe it's a little, if Google Mapper, Geographic Calculator, how that will affect the new NatRef systems coming out, how that would affect Google Mapper, old versions of the datums.
Okay, so when the new with NatRef, that's the horizontal component, and the new vertical component is going to be called NAPGD 2022 is the latest name. That may change to a later date since the publication has been delayed. That will show up as a new vertical datum. It is going to be distinct from NavD88. So it will, the abbreviation looks like NapGood. Up until now, all of these geoids, so geoids 96 up through 2018, these are all transformations to the North American vertical datum of 1988, basically evolving data that kind of like different realizations of a horizontal model. NAPGD, whatever the year it's going to be called, that is going to be a new model, not based on the old stuff. So that will show up as a distinct vertical datum, a distinct vertical coordinate system, and it will have its own geoids that don't directly relate to the others. There will, of course, be transformations between NavD88 and NapGD22, but it's not going to be just another iteration of NavD88. So great question. The piece nobody knows about quite yet is how time is going to factor in, because these will be the first time-based vertical coordinate systems to enter the database as well. So that part is going to be particularly exciting. But they'll all be entered in here as new coordinate systems. Because of the time changes, we're probably going to have to create a new type of vertical datum to handle that. Certainly it will need to be updated in Global Mapper, and without knowing what the final thing looks like, I can predict we're probably going to need to make changes to accommodate that. So global mapper and calculator would of course need to be synced up again at that future point.
Mm-hmm. There's a couple more questions here kind of relating to geoids, why they're the importance of keeping the various geoids and why there are multiple of them with different with the vertical datum.
Sure. So the geoids, here you'll see we've got, let's see how many we've got. We've got, looks like about 9 different geoids there just for one vertical datum. And the reason for those is some of these are for different geographic areas. You'll see one of them is for Alaska. So that one has, it's obviously separated from the rest of our country. So it's actually different subgrids based on completely different survey data. The rest of them are based on essentially evolving data that, in this case, the national survey authorities here in the US, the NGS, republish those periodically, just like they do the horizontal versions of NAT83. So each few years, as they sort of refigure all of the numbers that go into the horizontal systems, they're actually doing the same thing with the vertical systems. They improve over time as they roll out these new standards, factoring in better and better data with new technology. They republish the geoids, and so we get a better and better version of those vertical heights. Along with that, in any country, I'm using the examples here that are common to us, but in any country, these are defined by the national survey authorities. So in the case here of our US geoid, at one point in time, Geoid 1996 was the national standard. All surveyors in the country that were reporting elevations had to base their work on that set of geoids. Up through the years, the standard changes. And so we're at a present point now where the current standard has moved up to Geoid 2018. So the national coordinate system is called North American Vertical Datum of 1988, but to get there, you have to use the Geoid model of 2018. So it's essentially kind of keeping up with the Joneses in terms of your national standards wherever you are. So they do change over time. Periodically, sometimes in survey data you find poor data that's been factored in, or now with a changing picture you have better data at some future time. So there's room for those to evolve, and that's essentially the short version of the importance of those. Any others at the moment, Billy?
If you're actually going to use one of these geoids, how would you use this in GM? And does it change the nature of the attributes immediately in Global Mapper?
Okay, so that's a good segue. Let's actually hop over to Global Mapper at this point. So in the calculator, this is where we do the management of the coordinate systems. You can do test transformations using the calculator interface. We do have other webinars on how to work inside the calculator, but today we're primarily focusing on the Global Mapper side for folks that are new to this. Mm-hmm. So I'm going to hop over here into Global Mapper, and I'm going to step through this with a piece of lidar data, just because it's really easy for me to grab onto one particular point for illustration purposes. But the same ideas apply and as we're talking about vector files that are three-dimensional, that have elevations baked in, as well as raster files. The question there about attributes, I'm going to come back to that in just a bit as we're talking about some data, because attributes on vector files have one little extra piece here that we need to talk about. So in Global Mapper, I've turned on my GeoCalc projection mode, and I'm going to open up a data file. And I've already got this in my frequently used files list. So I'm just going to call it up from there. This is our typical lidar load screen. There's nothing special here about the GeoCalc mode. I'm just simply going to load this file in with all of its default options. If you've tuned into our webinars before, no doubt you have seen this piece of information. This is a subset of some of the national coastal LiDAR data that was flown around the time period of 2006 and 2011. It's about 1 meter point spacing, and this is a little sample around our Capitol building here in Maine. So the low area, what that shows up in blue is actually a river shoreline going up the hill here towards our Capitol building that I'm going to draw a path profile across. So this particular piece of data is really handy because it's got a point right up on the very tippy top of the dome of our Capitol building. So let's take a look at that point right there. If we crack into that, we'll find that that point is existing at 104.7 meters above something. And the something is the big question that we have here. So just take mental note here that this is above the 100 meter line. In the USGS definitions, all the metadata for these data layers, the LiDAR clouds, they define the vertical coordinate system for these as being on NAVD88. LiDAR is typically collected natively in ellipsoid height. It is a GPS derived position for those. If you're talking about aerial LiDAR, for sure. So they in the publication and processing of that data, it is put into a vertical datum from its ellipsoid height system. Now, the trick with a lot of LiDAR is that the vertical coordinate systems are not actually baked in appropriately to the metadata. So you're left with a question mark on the ups and downs of that. So this particular file, if we load this in and we take a look at the projection, so I'm going to open up, you can either double click on the layer or you can right click on that and choose options to get into the options menu here. I'm going to click on the layer projection tab. And this is where we always bring up our big scary warning that this is not how you reproject your data. This is simply how you define what it is coming in. So on our incoming coordinate system, we don't actually have a valid vertical reference for this. So it is simply assuming that it is ellipsoid height on the way in. And what I'm going to do is change this. So I'm actually going to put this into ellipsoid height. Right now, I know because I read its metadata that this is actually in NAVD88. But we need to put this into ellipsoid height so we can work with some other GPS data that we have. So to do this, you'll see we've got the vertical coordinate system already comes in for this. That part is handily predefined for us. But what I need to do is pick a different vertical coordinate system. So here's where our GeoCalc dialogues come up. I'm just going to shrink that down so we can see this is still a global mapper in the background here. Going to go down under North America, United States, and here's where we have all of those different vertical datums that we have. We have NAVD88 height, and this one happens to be in meters, which is what I need for the elevations for this data. And I'm going to hit OK. Now, as soon as that happens, it's going to pop open the secondary window. Because we have a default projection going on for the map, it needs to know how to relate those two. So this is one of the big pieces that GeoCalc mode adds on. It's the ability to pick your transformation going between the incoming system and whatever what we call the global projection for the map is actually based on. At this point, the transformation that it's going to need is the vertical piece. So you're going to see all of these vertical geoids for ways to connect the dots between NAVD88, which is what I've just said our data is, and the NAD83 ellipsoid height that is the basis of our global projection for the map. All of these geoids are what we just saw over in the calculator. And you'll see some of them are showing up in red and some of them are showing up in black. This little icon over here tells you whether or not these are in a usable state. And for most of the geoids, the reason these would be usable or not is because you have either downloaded the grids or you have not yet downloaded the grids. So on the laptop that I'm working on, I don't usually keep everything available because the geoids take up a lot of space. Honestly, they're really big grids. If you aren't using every geoid in the database, you don't need to have them locally installed. So you need to think about which ones you're going to be working with and make sure you have those available to you, and the rest you can basically leave. For any of those that you don't have locally installed, you can just simply right-click on one, and you'll see an option there to download the missing files. What that does is it reaches out to our FTP site, automatically downloads a zipped copy of all of those geoids and unpacks them into your calculator's data source archive. Once you've done that, it will instantly turn black and you can use it for transformation immediately. So the ones that I'm going to be working with here, US Geoid Model of 2018, I've already downloaded that, so it is available to me, and I'm just going to say okay. And then on the dialog here, you'll see the coordinate transformation has actually filled in. So it now knows how to relate the coordinate systems that I have involved on our map. So I can okay that. It's going to bring me back out to our map. Nothing at this point has actually changed, and this is where, for those of you who are long-time global mapper users, when you pick the coordinate system, things change immediately. It reprojects on the fly. Vertical transformation is a bit heavier of a process, so we don't actually modify the heights until we write something out. So a best practice is, if you are going to be working with data sets that factor in multiple datums, the best workflow is to bring them through here, pre-process them into the datum you're actually working in, and then bring them all back into a common workspace. Because we're not able to do that vertical transformation on the fly. It's a pretty heavy process. So if we take a look now at our what we call our global projection inside Global Mapper, you'll see the global projection is still ellipsoid height. So heights that are referenced in the attributes, all of our surfaces that we're talking about, those are all ellipsoid height, but I've now identified the incoming layer as being something else. So the transformation we set up was from the incoming layer to the global projection. In this case, it's ellipsoid height based on my horizontal datum of NAT83. So I'm just going to cancel right out of there. And what we're going to do is write this out. I'm going to create a new file. So I'm going to export out our lidar data. And I last used last, so that's coming back up for me here. You can just simply pick whatever that is out of the list. And it's going to ask us what we're doing here. So all of our usual export operations, there's a vertical coordinate system that you'll see in there. And there's a little note here that this does not actually control the export at this point. This is what you're using for labeling within the metadata of the file. So this one is picking up NAVD88. And the reason we do this is actually because there are some data formats that aren't able to handle all of the appropriate coordinate systems that we need. So very commonly, what a lot of folks will do here is just simply set it to none. You can make the choice that you need for the file types that you're working with. Some file types expect something that may not be there. So we're going to set this to none for this particular workflow and go ahead with that export. And I've got my little test file waiting here for me. So I'm just going to make a new layer called ellipsoid height. And I'm going to save that out. So you'll see it does an export process. It doesn't take super long to write that out. Doing the transformation on the way, it's just enough of a hiccup so that we don't want to do that on the fly as we're going. And now what I'm going to do is we're going to get rid of that layer, And I'm going to bring in my file that we just wrote out there. So here's our new ellipsoid height layer. And I'm going to do that path profile across the roof there again. And now if you notice, the peak of our roof is now less than 100 meters. It's down here below 80 meters. So the separation there between our ellipsoid height reference and our sea level based reference of NAVD88, the ellipsoid height in this particular part of the world is much higher than the sea level reference. Conceptually, sea level is a much easier idea for people to think about because the ellipsoid itself doesn't really relate too closely to where that low sea level for coastal regions, particularly where we literally have a sea level river at the bottom of this data set. The peak of this is about 20 meters, a little more than 20 meters offset from our sea level. So we've dropped from an elevation reference of 104 meters down to about 79 meters. That doesn't mean our data is lower. What that really means is that our zero reference was put up at a higher level. So the data is in the same place. It's our description of that data that is changing. Now, whether we've done this on a piece of lidar data, whether we've done this on a raster file, vector file, the process is actually the same. The only part of this where things get a little bit different is in the context of vector files that have attributes. So if I'm just going to grab onto my info tool and pull out one little piece here. Let's pretend for a second this is a shape file and it has your usual attributes. So you'll have things like an elevation listed in the attributes of your vector file. Text-based attributes that are the elevations in there are not updated when you change your vertical reference. So if you're doing a transformation on your data and you also want your elevations to match, you're going to need to go back through once your data is transformed for output and pull out the elevations. So you're going to be using some of those tools in the digitizer, like get elevations from the actual geography of the layer to update those fields. That's an important last step that some folks miss out on when they're trying to update vector file based stuff in a different way than we do for lidar or raster. All right, covered a lot of stuff there. Billy, we got any questions coming in?
We do have a couple. Maybe we'll start with a little easier one to answer. Can you show if there are any geoid grids available for Europe?
For Europe, yeah, let's take a look there. So we do have one trick of navigating the database in here is and this is a real mind bender, but there are vertical coordinate systems for which there are no geoids. So it's important to look in two places. When we look in the coordinate system definitions, you'll see categories for places like Europe. So if you click on the Europe level there, you'll see a list of vertical coordinate systems that apply for large regional areas. And if you are looking for something that is a much, much smaller localized area, like say Luxembourg, you'll have a subset for just what's contained in that area.
Mm-hmm.
Now, just because there's a coordinate system defined for an area doesn't mean there's actually a geoid for it. So this is where you get into a little bit of research. The geoids that are available, you can easily find under the coordinate transformation definitions. And incidentally, you can also look these up on GeoCalc Online, which is our web-based repository for coordinate systems. But the same lookup there, you can come down under the transformations and say, just show me all of the regional systems for Europe, and you'll find those particular transformations. And finding the specific transformations are the complicated piece, because some of these go between particular coordinate systems and not others. So it's important to find both sides of the transformation that you need in one definition. We can connect the dots here if you have two transformations to get there. So there is a little bit of extra flexibility. Sometimes that happens if you're going from, say, an ellipsoid height to a geoid, and then from one geoid to another geoid in a little chain to get there. We can do that too. If you're new to Calculator and you're having a hard time finding the particular systems you want to be working with, please contact tech support. We do this all the time. We can help you research whether or not a geoid exists for a particular spot, and we're glad to help. If you're looking at Geographic Calculator and you're trying to make sense of it, same thing. Even if you don't yet own a license, feel free to contact our tech support, and we can guide you in whether or not a geoid exists for a particular area.
That's where I come in, right?
That's where Billy comes in. There we
go. There's a couple more here. I'm gonna squeeze in a little more lengthy one. There's one question here. They're using USGS digital terrain models derived from lidar. They're using for their base maps and using ortho data collected from a drone. They're updating the terrain using the drone data for the USGS. So sometimes, would you think using GeoCalc mode would work better for doing that process, or?
So let's see. You're using USGS. Maybe slow walk me through that one again.
Oh, sorry.
They're using terrain models from the USGS.
Correct.
And they're augmenting those with drone-based terrain data.
Yep. So so data they collected from a drone, and then using that to update the USGS terrain.
Okay, I see. So the drone, there's going to be a lot of play there with the accuracy of the drone data. Typically, drone-based terrain data is much more granular than terrain data that we have from the national sources in any country. So in the US, in the US data that we have, a lot of our terrain models, the really good ones are down to about 2 meters of resolution, whereas a locally collected drone data set could be a matter of centimeters. The level of granularity that you're going to get with drone data to augment that, if you're seeing shifts around the edge, one of you end up getting into workflows where you're going to be blending them into each other. Transformation may or may not clean up the whole issue. If you basically, you'll typically see like a step at the edge of the data where you go from your very sharp resolution stuff to your broader resolution stuff. And in the case of drone data versus national map data, you're talking about like 10 to 1 on the resolution differences in between those. So your best bet is probably going to be a combination of blending and making sure they're on the same source. So your drone data, if you're using surveyed ground control targets, those are going to be on some vertical datum reference. And if it's in the States, you're probably working on NAVD88. You're probably working on Geoid 12 or Geoid 18. Geoid 18 is the current standard. Just a geoid transformation is never going to completely make those steps at the edge of the data disappear, and it's purely because of the differences in resolution of that data. If you're working with survey grade stuff in both systems, you're still going to need to do a little bit of a blending process around the edge, and that's a raster process where you simply take the two values that are there and you feather them into each other to handle the slopes. I'm thinking of there's several ways this conversation might go, and I'm not sure I have enough information to fully answer it. So please, if I haven't answered your question, follow up with us with the tech support group, and we can go a lot deeper on that.
There's another question that kind of is kind of a similar vein. Can you use any of these vertical transformations to transform point clouds generated from our own pixels to points tool?
Yes, definitely. So again, that's the reference is going to depend on what your controls are, how your particular drone system does its ground controls. If you're working with ground targets and you're georeferencing your point clouds that you're generating, those are probably either going to be in ellipsoid height, or if your ground controls are locating those against like NAVD88 here in the States, or whatever you're using in any other country. Once you've established a proper vertical reference, essentially the world is your oyster. You can transform to or from whatever the appropriate coordinate systems are anywhere. So whether that's a worldwide geoid model like EGM 2008, at a very low resolution, or whether you're working with on the ground survey data where you're talking about sub-centimeter accuracy, all of those transformations, once you've got your vertical reference properly defined, it's whatever combination you have available, you can do those transformations against any type of data, whether it's point clouds, typical GIS vector data, or three-dimensional raster data.
Great. Do you want to take one more before we hit 3 o'clock, or?
Yeah, let's go ahead and we'll do one more, maybe two, depending on how long it gets into.
Okay. Can you illustrate the when you're not in GeoCalc anymore? Can you see the NAVD88 values in Global Mapper?
Oh, okay. So if you're if you've got GeoCalc set up and you're doing the transformational work and you're, say, giving it to somebody else, what do they see when you're done? So I've now taken this data and put it into ellipsoid height. If I toggle off my GeoCalc mode, you're going to see this window pop up, and it's going to say it needs to restart. So if you've saved or not saved, whatever you want to do with your workspace, it's going to prompt you to continue there. But Global Mapper is going to need a quick restart, and that'll come right back. And what does that look like now that we're done? So still the same lidar load screen. The data itself looks the same. And if we want to do that path profile again, we natively put that data onto a new coordinate system. So that peak of that building is still below that 80-meter mark. So we did the transformation. We can play with this data away from GeoCalc mode, and it is what we transformed it to. It's not going back to anything else. If you go back and take a look at the layer projection for that, again, you get your scary warning that don't use this to reproject. You're just defining how we interpret the data. You'll see the old school Global Mapper projection. So if you notice, the question was, what happens to the NAVD88 data? NAVD88 isn't anywhere on here. We actually put it in ellipsoid height anyway, but the vertical coordinate system is gone. The data itself is still there, but Global Mapper doesn't know how to handle any of those vertical transformations. In terms of the coordinate system, Global Mapper is effectively a two-dimensional application without the GeoCalc mode tools augmenting that, adding on all the geoid support. So let's go ahead and we'll do one more, and then we'll wrap it up. And any other questions that have come in, if we haven't had time to get into those, we'll be following up via email with those folks.
This one isn't specifically GeoCalc mode, but can you create user-defined systems with the Geographic Calculator?
Okay, yes, that's a good one. The answer to that is definitely yes. You can create a user-defined grid, and let's see. This takes a few minutes to show. It's in the documentation, so I'm not going to step through the whole process here. But I think I actually have piece of data I can just really quickly show this with. So I'm putting my GeoCalc mode back on. In my sample data, this is something I do occasionally show folks. I have a chunk of a geoid. This is actually a tile of NavD88's geoids. This is a piece from the New England region, and if you look at it, it is really flat. You notice there's no terrain here, there's no mountains, nothing like that. So this is simply a tile of offsets between ellipsoid height and NavD88 over a large region here. If you take a look at my longitudes here, we go from 78 west all the way over to 60 west. Once you have your control data, so I'm assuming that you're a surveyor if you're asking this question. If you have your regional control data and you have turned that into a raster grid, you're going to have a nice huge area, I assume. Some folks do these over small areas as well, but you're going to need your control data to make those offsets, representing the vertical offset between ellipsoid and your whatever your vertical datum is going to be. We're going to need to export that as an elevation grid format. And in that elevation grid format, you're going to find a file called Blue Marble Gridded Data. That is how Calculator recognizes the geoids, and you can then go into the Geographic Calculator in the vertical coordinate systems and use the plus button in there to add your own coordinate system. You're going to need to add your datum, your coordinate system, and then you'll add a transformation. And you'll in that transformation, you'll specify the grid file that you produced in Global Mapper. That will be a fully custom geoid, and you can do all of the same types of things with that. So that was a great last question. So at this point, I think we're gonna wrap it up. And again, if we have any other questions coming in, we'll follow up with those via email directly to you. So thank you everyone for attending today. Thanks a lot, Billy, for helping me out with all those questions.
Yep, thanks Sam for presenting it all and answering those.
All right, and we're gonna call it good for there, and we'll see you next time.